Hey guys, welcome to Chandler Science, 2020 Momentum Exam Corrections for my class. This video is going to be all the multiple choice questions and the solutions to all the questions. So follow along, correct the ones you missed. Remember, you're going to write down the ones you missed, what you put, why it's wrong, why you answered that, what was your misconception, misunderstanding, and then the corrected answer in your own words or show your work. All right. So let's get right down to it with number one. Oops. There we go. Number one, we got a 1 kilogram lump of clay sliding to the right on a frictionless surface with speed 2 meters a second, collides head-on and sticks to a half-kilogram metal sphere that is sliding to the left with a speed of 4 meters a second. What is the kinetic energy of the combined objects after the collision? All right, so collides head-on and sticks. So this is in order to solve this one, we're going to have to first start with the conservation of momentum. We're going to try to find the kinetic energy after the collision, but in order to do that, we need to know what the velocities of the objects are after the collision, right? So we're going to have 1 kilogram clump, so we're going to use mv1i plus m2v2i equals, and say collide and stick, we're going to combine their masses after the collision. That's a 2. For one final velocity at the end, right? This is our conservation of momentum formula. Shouldn't be anything new. So the clay is 1 kilogram. Its velocity is 2, plus mass of the sphere is half times velocity, which is -4. It's going to the left. We got to keep in mind direction here. So we have 2 positive to the right, 4 to the left negative. Combined mass is 1.5 times velocity VF. That's the left-hand side is 2 minus 2 equals 1.5 VF. 2 minus 2 is 0. So that means that our final velocity is going to be 0. So we divide by 1.5. Since there's 0 over here, 0 divided by anything is 0. So our final velocity is 0. Well, if we have 0 final velocity, our kinetic energy has to be 0 because we're not moving, right? Kinetic energy K is 1/2 mv squared. Well, its velocity is 0. 0 squared is 0. Times m is 0 times half is still 0. So the kinetic energy is going to be 0. There is no kinetic energy. So the answer is D, 0 joules. All right. This would definitely be an inelastic collision because we are not conserving our kinetic energy we had before the collision. So there you go. D, no, 0 joules. All right. Number 2, a 12 kilogram box sliding on a horizontal floor has an initial speed of 4 meters a second. Coefficient of friction between the box and floor is 0.2. The box moved the distance 4 meters in 2 seconds. The magnitude of the change in momentum of the box during this time is most nearly what? All right, so we're looking for the magnitude of the change in momentum. All right, so that is impulse. And why is it not going to pin automatically? That is annoying. All right, so 2 ways to find, that's supposed to be a delta P. 2 ways to find delta P here. Our impulse is force times time, or we can use delta P is mass times the change in velocity. What do we got here? Well, we got an initial speed, VI. We have a time, 2 seconds. We have a distance, 4 meters. We have a coefficient of friction, mu. What are we going to do here? A couple options. I'm going to go ahead and find out what the force of friction is on this. We have mass too. Force of friction. What's the force of friction? The only forces on this object that are actually doing work is the force of friction, right? Normal force and gravity are cancel each other out. So friction is doing work. So force of friction is mu times the normal force. Well, this is a flat surface. This is a horizontal floor, which means that the normal force up is the same as the weight down. Well, this is a 12 kilogram block. So its weight is 120 newtons, which means the normal force is also 120 newtons. So it's 120 newtons times the coefficient of friction 0.2. That's going to be a force of friction of, and I can't do math in my head, so I'll punch it in, 24 newtons. 24 newtons of friction force. So now I'm going to go ahead and use this equation here. Now that I know what the force is, again, the only force being applied to this thing is friction. Or the only force doing work, I should say, is 24 newtons times the time. Well, it's 2 seconds, it says. That's that equation. That gives my delta P. Or my change in momentum, my impulse, 48 kilograms times meter per second. And there we go. Answer is B, 48. All right. Alright, cool. Number 3, a ball of mass 0.4 kilograms initially at rest on the ground. It is kicked and leaves the kicker's foot with a speed of 5 meters a second in a direction 60 degrees above the horizontal. The magnitude of the impulse imparted by the ball to the foot is most nearly what? Same kind of question as before. This time we got, why is it not going, why it's changing to the cursor? I don't like it. I got to select pin every time and go to there. Do it automatically. Why do I got to keep doing that? Is there a way to, like, you know, keep it locked in or something? I don't know. Alright, anyway, so this is also a change in impulse problem, or change in momentum, sorry, impulse problem. Force times time is one option, or mass times the change in velocity. I'm going to use this one this time. A lot of students got confused here because they thought the angle meant something. This angle is a distractor. It's asking for the magnitude of the total impulse imparted by the ball to the foot. Well, we don't care about the angle here. There's no angle on any of these equations, right? Well, actually, I guess technically there could be, but I'll get to that later. It's just mass times change in velocity, right? We don't care what the direction we're going in. So the ball is going to go up at an angle, right? 60 degrees to the horizontal like that. It doesn't matter what the angle is. Does it have components? Yeah, it does. And you could find those components if you wanted to. What we're looking for is this resultant vector, right? The total momentum imparted to the ball by the foot, or its change in momentum impulse. So we're going to find, we know the mass of this ball is 0.4 kilograms. We know its final velocity is kicker's foot with, yeah, it leaves the kicker's foot with 5 meters a second. It was at rest initially, so initial velocity is 0. That's going to get us our delta p. Delta p equals 0.4 times 5 minus 0 is 5 times 4 is 2. So 2 Newton seconds. Or Newton seconds are the other unit for the other unit for impulse was Newton seconds. So there you go. 2 Newton seconds of impulse to the ball. All right, that's number 3. Number 4. This is probably the most missed question, or one of the most missed questions on the exam. So let's take a look here. At time t equals 0, we have 2 figure skaters are moving together over ice with negligible friction, as shown above. Skater 1, represented by the large black dot, is twice as massive as skater 2, represented by the gray dot. At t equals 2, the skaters push off of one another. The location of skater 1 is shown at t equals 4 seconds. The location of skater 1 is shown at t equals 4 seconds. At t equals 4 seconds, skater 2 is located at which of the labeled positions? All right, so where does skater 2 going to end up? In order to do this problem, we have to think outside the box a little bit. It doesn't tell us the masses, right? But it does tell us that the black dot is twice the mass of the gray dot. So I'm going to make up a mass of the black dot and say that its mass is, I'll call it black dot, its mass is 2. And the mass of the gray dot is 1. It's twice as much, right? Sure, it works for me. What about these vertical lines in this little chart they gave us? They don't tell us what they are, right? Is it 1 meter apart, 2 meters, 10 meters, half a meter? We don't know, and we don't care. The point is that they're equally spaced. So I'm going to assume that each, and it didn't, so you can make up whatever number you want here. I'm going to call them 1 meter apart. If you wanted to make them 10 meters apart, you could. The point is that they're all 10 meters apart, right? So this is like 0, 1 meter, 2 meters, 3 meters, 4 meters, and so on. If you wanted to be 10, 20, 30, 40, 50, you could do that. I wouldn't recommend it, but you could. Just makes your math that much more complicated. But the point is they're evenly spaced. So we're going to make up a number. So I'm going to say it's 1 meter apart. If they are 1 meter apart, then what is their mass of the combined skaters' velocity before they push off each other? Well, look, we go 1, 2, 3, 4 meters. Do it again, so you see it better. We go 1, 2, 3. I can't draw. 1, 2, 3, 4. It's still terrible. Whatever. You get the idea. 4 meters in 2 seconds, right? Well, what speed is that? If I go 4 meters in 2 seconds, I'm going 2 meters per second. So the initial velocity of this skater is 2 meters a second, and if I assume that the distance is 1 meter apart. So I got an equation now. I'm going to say my initial mass, my combined masses, I mean, of the 2 skaters added up, the black dot plus the white dot, or the gray dot, times their initial velocity of 2 is going to equal the mass of the black dot times velocity of the black dot plus the mass of the gray dot times velocity of the gray dot after the collision, right? This is final. All right, and now I know the velocity, I know the masses, I know this initial velocity, so this is, add these two up, 2 plus 1 is 3 here. My initial velocity I figured out is 2, equals, mass of black dot is 2. And now we run into this, what's the velocity of the black dot after the collision? Well, again, guys, check it out. If we assume, we know these are all evenly spaced, right? How far does this black dot go? From here to here, it's going to go 2 meters, right? 2 meters. How long does it take? Go 2 seconds here to 4 seconds. So it goes 2 meters in 2 seconds. Well, that's 1 meter a second, right? All right, plus mass of the white object is 1 times its velocity, which we don't know, as we're looking for. And we're going to solve for 3 times 2 is 6, equals 2 plus 1 minus 2 both sides. We get 4 equals 1 times VF, or just, VF on the gray dot is 4. So if the velocity is 4, how far will the white dot go from here to over here somewhere? Our initial time here is 2 seconds. That's when they push off each other, to 4 seconds. So it's got 2 seconds to operate. It's got 2 seconds to move, right? Where's it going to end up after those 2 seconds elapse? Starts here at t equals 2 seconds, and it's going to end at t equals 4 seconds. Well, if its velocity is 4 meters a second, it's going to go 1, 2, 3, 4. 1, 2, 3, 4. It's going to end up in position D, which is your correct answer. All right. That's number 4. Moving on. Number 5. A person of mass 60 kilograms sliding along level ice at a speed of 3 meters a second collides with a second person who was initially at rest. Assume that friction is negligible. If the two people hold on to each other if two people hold on to each other and their common final speed after colliding is 2 meters a second, what is the mass of the second person? All right, so this is just a conservation of momentum problem, pretty straightforward. Nothing too fancy here. Look at a mass of 60 kilograms plus some other, oops, no, that's after the collision, times velocity, of, 3, plus second person who is initially at rest, so they have no momentum before the collision. After the collision, they're now combining their mass, so 60 plus m, we don't know the mass of the second person, times 2, because their velocity after the collision was 2, so it's 180 on this side, equals, distribute the 2 here, 120 plus 2m, and minus 120 both sides, I get 60 equals 2m, divided by 2, and I get m equals 30 kilograms. The answer is B. So pretty straightforward on that one. All right. Number 6. Gotta change to my pen. Wonder if I unplug my thing and plug it back in, it'll I'm gonna try that in a second. A projectile fired into the air explodes and splits into 2 halves of equal mass that hit the ground at the same time. If the projectile had not exploded, it would have landed at point X. All right, this one, guys, I gotta draw a picture. So I'm gonna draw a picture for you. This helps me a lot. Okay, these conceptual problems really helps me draw pictures and diagrams and kind of illustrate what's going on. So I shoot this thing up in the air. Right, it goes, lands here. Okay. Now it says that if it had not exploded, it would have landed here at point X, right? Which is a distance r from here to here. Look at that straight line. That's pretty good. That's a pretty good straight line. A distance r. All right, I get excited about straight lines and good circles. All right, so if it hadn't exploded, it would land here at point X. All right, after the explosion, though, okay, but it is exploding, right? So after the explosion, one of the halves lands at point Y, which is a distance 2r to the right. So, okay, so now when it does explode, this is when it doesn't explode. Doesn't explode. It lands here. The whole piece lands here. If it does explode, one of the pieces lands here at point Y, half of the piece, right? At point Y, and this is a distance 2r. So another r here, right? So if we add them up, r plus r would be 2r from Y back to the launch point. This is a launch point. Okay. So I want you guys to think about this for a minute. The key here is recognizing that when the object does not explode, it lands here. Okay. Now that means, guys, that where is the center of mass? the center of mass is flying through the air. The center of mass of this object, right? Whatever this projectile is. Okay, let's say it's a rock. It doesn't matter what it is. The center mass of the rock system is in the center of the rock, right? So the center mass has to be here at point X. This is center of mass, all right? Otherwise, I think the symbol they use in the book is a little like cross, a circle with a cross like that, I think. That's center of mass, right? This is the position of center of mass. That center of mass position cannot change, right? The only way the center of mass of a system can change is if there's some outside force from outside the system that does work on the system. There's no outside force here. It's going to explode. That explosion force is coming from inside the object, whatever it is. Maybe it's a grenade or something. I don't know. But it's coming from inside this projectile, so it's no other outside force doing any work here. Okay. Well, if I got half the mass at point Y, right? I still got half the mass here at point Y, which is 2r away. The other half the mass has to be here at the launch point, because I got half the mass. If half the mass is here at the launch point and half the mass is here at point Y, where's the center of mass? It's still in the middle where it needs to be at point X, right? Right in the middle. That's what the center of mass is. So that's why the answer is at launch point B. That's where the other half of the projectile has to land. Okay? Kind of a weird problem, but hopefully that makes sense. Okay, moving on. Number 7, a toy cannon of mass 1 kilogram is initially at rest on a horizontal surface. Draw a little cannon. Oh, I was going to unplug. Okay, let me try this. Maybe this will work. I don't know. Just going to reset this. Okay. And nope. I don't want to have to click it every time. It's so annoying. All right. Okay, toy cannon. So I got a little cannon here, or whatever. Okay, there we go. Toy cannon initially at rest on a horizontal surface. So here's the surface. It's going to launch a 0.05 kilogram projectile. All right, it's going to launch projectile in this direction at an angle of 60 degrees above horizontal. So this angle, 60 degrees, at 10 meters a second. Oops, 10 meters per second. What is the speed of the 1 kilogram cannon immediately after the projectile is released, assuming that friction is negligible? Alright guys, so we got to recognize this is kind of a two-dimensional problem. Here's the thing though guys. The momentum of the cannon is going to have, this has two components, right? Let's look at these components here. It's got, the projectile has two components. It's going up this direction, a little more vertical I guess, because it's 60 degrees. Erase that. Alright, so it's like more like this. So it's going to have a horizontal component. Let me get my colors. Oh, I don't want a highlighter. Silly. It's going to have a horizontal component, green, and a vertical component, red. Christmas colors. Right? Now, when this thing fires, right, so if the ball goes up and to the right, that means it's going to push the cannon down to the left, right? Here's the thing, guys. Can the cannon go down? Can the cannon go down into the ground? I mean, maybe if it's like in quicksand or like, you know, in water, but it's not. It's on a horizontal surface. It cannot go into the ground. Okay, now, technically speaking, that momentum's got to go somewhere, right? It goes into the earth in this case, and it's going to, you know, apply its momentum to the earth, which is going to do nothing because the earth has such a massive, you know, mass that it does nothing. But this component here, right, so this is the momentum, that's the momentum of the ball. So the momentum of the impulse on the cannon is opposite that, right? So it's going down this way. So this component down does nothing, but the component here is going to do something, isn't it? So we only really care about that component, okay? So we're going to find out what this green component of velocity is. So cosine 60 is a half. This is the cosine, right, because it's adjacent. So this is actually 5 meters a second. So what we're going to do, now that we know that we have 5 meters a second of velocity for the cannonball in that direction, and since the cannon cannot go down, it can only go to the left because it can only roll this direction, right? Because the ground's in the way. We're going to do conservation of momentum for the horizontal direction only because the cannon can't go vertically, right? So the mass of the cannon is 1 times my initial velocity, which was 0, plus the mass of the ball, which is 0.05 times its initial velocity, which was 0. Right, so everything's 0 initially. Now we only care about the x component here, the horizontal component. So the mass of the ball is 0.05 times the mass of the ball, the velocity of the ball in the x direction, which is also 5, plus the mass of the cannon, which is 1, times its velocity in the x direction final. All right, so on the left-hand side we got 0 equals 0.05 times 5 is, what's that, 0.25? Plus 1 times VXF, minus 0.25. It's asking for the magnitude or speed. Speed has no direction. Speed is a vector, so we don't care about direction here. So it's going to be negative 0.25 is the actual speed, right? Because dividing by 1 does nothing. So it's negative 0.25 meters a second. Just subtract this over here. But it's, again, speed is a scalar quantity, so it doesn't have direction. So we don't care about the negative sign. The answer is A, 0.25. Okay? And that's how you get that. So earlier I was talking about, earlier in this problem back here, I was talking about how, like, you know, the direction doesn't, the angle doesn't really matter. In this case, it didn't matter because we're doing the resultant vector. But, you know, you can have change in input. Your impulse and your momentum can obviously have components, as we've discussed in class. So we've done two-dimensional problems before. The only thing is that in this problem, the vertical component didn't do anything because the cannon can't move vertically because the ground is in the way. So only the horizontal component mattered. Hope that makes sense. Let's move on to number 8. An ice skater is moving at a constant velocity across an icy pond. The skater throws a snowball directly ahead. Which of the following correctly describes the velocity of the center of mass of the skater snowball system immediately after the snowball is thrown? Assume friction and air resistance are negligible. Alright, so here's the thing. Still gotta click my pen. Alright, so I got the skater, right? Here they are. And they're holding a snowball in their hand, right? Now, if they don't throw the snowball, let's say that they just decide, you know what? I'm not gonna throw the snowball. I don't feel like throwing it. Screw you. I'm keeping the snowball for myself. Where's the center of mass of the snowball person system? Isn't it basically like in the center here? Okay, let's make it a color. Let's do a color. Let's go with, how about a nice thick red? So center of mass is here, right? And that big red dot. Basically in the center of the person, because the snowball's mass is very small compared to the person. So the center of mass is basically in the center of the person. Now if the person starts skating to the right, you get a velocity this way, right? You know, now a few seconds later, now the skater is here. Snowball's in their hand. Where's the center of mass now? Isn't the center of mass still basically in the same position? So the center of mass also has velocity, right? The center of mass's velocity in this case is the same as the person plus ball's system center velocity. So they're the same, right? But now the guy, the skater or whatever he is, skater is now he's like, you know what? All right, fine, I'll throw the snowball now, okay? Well, if the skater throws the snowball, he throws the snowball. Now the snowball's over here. Got a velocity going that way. Remember, the snowball's momentum or mass is very small. But you guys remember we were on the thing with the skateboard. Now, in first period, it didn't work so well because there's too much friction, but I got it to work in other periods. If I'm on a skateboard with very low friction and I get a heavy ball and I throw it. Now, remember, this is an icy pond. They tell you icy ponds, they're basically telling you ignore friction, right? So imagine I have a frictionless surface. I take a ball and I throw it this way, right? What's going to happen to me? You guys all know this instinctively, right? You kind of roll backward, right? It's the recoil effect. I throw it forward, I'm going to slow down a little bit. So when the skater here throws a snowball, the skater himself will lose a little bit of velocity, right? Because he gave some momentum to this ball. This snowball now has greater velocity than he does, so he's going to slow down a little bit. But remember that guys, has there been an outside force at play here? No. The outside force is no outside force that's doing anything, which means the center of mass must have the same velocity as it did before. It's still going the same speed, right? Now the center of mass is going to kind of drift away from the skater a little bit, slowly, because again, the skater's mass is still much more than the snowball's, but because the snowball is now way out here and moving further away every second, the center of mass is now going, since it's going the same speed as it was as if he hadn't thrown the snowball, and the skater slows down a little bit, the center of mass is going to kind of drift away from the skater, maintaining the same speed it had before as if he didn't throw the snowball, right? It has to. The center of mass never changes. Nothing about the center of mass changes unless there's an outside force that does work on the system. An outside force must do work. So whatever the center of mass's velocity is, whether the center of mass's position is, all that stuff's going to be, the same and constant unless an outside force does work. There's no outside force at work here. The skater himself is the one throwing the ball, so it's not outside. It's not an external force. So the velocity of the center of mass is the same as it was before, as if nothing ever happened. And that means that the answer is, of course, D, equal to the original velocity of the skater. Number 9, object X. We got a graph here, velocity time graph. Object X travels. Almost all students got this one correct. So real quick, object X travels across a horizontal surface and collides with object Y. The velocity is a function of time for object X and Y are shown in the graph before, after, and during the collision. Both objects have a mass of 2 kilograms. Which of the following is correctly describes the momentum P of the system and the kinetic energy K of the system? Well, I can just look at this picture and tell you that K is not conserved, right? I mean, look at the velocities. I have a velocity of 2 for the white, unshaded circle. And remember, kinetic energy, the velocity is squared, so it doesn't matter that it's negative. It's become positive anyway. So I got a velocity of 2 before and 4 for the other one. We add those up to find total kinetic energy, right? After the collision, what's my velocity for both objects? It's 1. They both lost velocity. So there's no way kinetic energy can be conserved. The only way kinetic energy can be conserved is if one object gains some velocity while the other one lost it, right? And then maybe it kind of balances out. But if they both lose velocity, there ain't no way we can maintain our kinetic energy from before the collision, right? They're both losing so much energy. So we know K is not conserved. So we can rule out A, because A says K is conserved. We know that can't be true. And we can rule out C, because that says K is conserved also. So it can't be A or C. So now the question is, well, is momentum conserved? Well, I mean, of course it is, because momentum is always conserved. But if you want to prove it to yourself, you can. Let's find the momentum of the objects before the collision. So the black object has both of them have the mass of 2, it says. So the black object, this is before collision. Just add them up. Black object is mass 2, velocity 4, plus mass 2 for the white object times a negative 2. This is 8 minus 4, which is 4. And then after the collision, we have mass of 2 for the black object times the velocity of 1, plus mass of 2 times the velocity of 1. Positive now. And this is 2 plus 2, which equals 4. 4 and 4. Momentum is conserved. B. All right. Number 10. How does an air mattress protect a stunt person landing on the ground after a stunt? This is the most correctly answered question, so good job. The answer is E, of course. How do we know it's E? Remember, guys, we talked about this a lot during lecture. We watched videos of the car crash. We talked about how, if you jumping off a building, right? So here we are. Let's do a quick picture here to illustrate my point. If I could erase this real quick, a little better. Okay, so here's a stunt guy. He's gonna jump off here. Woo! Bam! Lands. Now, if you have no cushion, you land on the concrete, the ground, whatever, right? That impact is gonna be very, very quick, right? All the impact, bam, all at once. It happens in a blink of an eye, right? Less than a millisecond, let's say. All right, so what's your change in momentum? Well, your change in momentum is going to be your force. Let's say it was, I'm going to make up a number just to make it easy, 1,000 newtons times the time it takes. So let's say it took a 0.1 second, right? So that's going to be a delta P of 100. Now, if you do land on an mattress or whatever, right, to cushion your blow, now you have a mattress. The time goes up, the force goes down, but the delta P remains the same. It's the same impulse, right? You're still going from whatever velocity you had to no velocity, right? You still come to a rest because you hit the ground, right? You just come to a rest at a little bit longer time because you got that extra cushion to pad your landing because you're landing on that on the mattress. So let's say it makes a time from 0.1 to 0.5. Well, 0.5 instead of 0.1. Remember, the impulse must be the same. So the impulse is still 100, so what's the force going to be? Well, now 100 divided by 0.5 is 200. So yeah, my impulse went down, my force went down by a lot. My force was 1,000, now my force is 200, so it went down a lot just by changing the time a little bit. So the whole point is that we're going to lengthen the stopping time, right? We're going to make time larger from, like, for example, from 0.1 to 0.5. If you make time bigger, the force that they feel has to go down. The impulse is the same, but the force they experience goes down because they're kind of spreading the force out over a period of time instead of it all happening at once. All right. All right, guys, with math part 2, had to take a hiatus there and go to bed. So I'm going to do 11 through 20 now. Let's wrap it up. Got number 11 here. 11 is a weird one. There is no correct answer that is listed. A, B, C, and D are all incorrect. I double checked this like about 100 times, and I think I'm right. So let's go over and see why that is the case. So we have ball X of mass 1 kilogram and ball Y of mass half a kilogram traveling toward one another on a horizontal surface. Both balls travel at a constant speed of 5. So we got ball X here going this way, let's say, and ball Y, let's say, is going this way. So they're going at each other, right? We're going to say ball X's mass is 1, ball Y's mass is 2, and they both have velocity speed of 5, but velocity of X initially is positive 5, and the velocity of Y initially is going to be negative 5, right, because it's going the other direction. During the collision, ball Y exerts an average force with a magnitude of 40 newtons for 1/6 of a second on ball X. So that means delta P, the impulse, change in momentum of ball X, is going to be negative 40 times 1/6. Why negative? Well, look at the direction they're going. We have defined to the right as positive, which means that left is negative, and the force that Y exerts on ball X is going to be to the left, right? Because ball Y hits it, pushes the ball X to the left. So negative 40 to the left. And it says magnitude, right? That's why there's no negative sign here, because we get to define how direction works, right? So this is going to be delta P for that ball of a negative 6.67. I believe that is the correct number. Let me just triple check. Yep, so I'm just doing 40 times 1/6, and I got 6.666666, which we'll round that up to 6.67. Negative for direction. All right, now that means that the impulse on ball Y is equal but opposite to the impulse on ball X, because that's how momentum works. It's always conserved. So the impulse on ball Y will be a positive 6.67. So we're trying to find out what the velocity or speed of ball Y is after the collision and which direction it's going in. Well, we know now that the momentum, or the change in momentum impulse of ball Y is 6.67, positive now, right? Because ball X is going to push ball Y that way. Equals the mass of ball X, which is 0.5, times the velocity final, which we're looking for, minus the initial velocity of ball Y. But remember, it was negative 5, right? So minus 5 here. So it's going to be 6.67 equals 0.5 VF plus 2.5, right? Because a half, just distributing the half here. Half times VF, and then minus a negative is positive, so VF has a positive half of 5 is 2.5. I'm going to subtract 2.5 both sides. Oops. And I'm going to get 0.5 VF equals, let's see, what is 6.67 minus 2.5, and I get 4.167. Divide by a half both sides to get rid of that VF. To get rid of the half, so VF by itself, and VF is going to be 8 point something, 8.33333, 8.3, repeating meters per second. So, positive velocity, right? Which means ball Y gets knocked back this way, and it's greater than 5. Is 8 is greater than 5 here, obviously, and it's going the other direction that ball Y was going. So the answer should be greater than 5, but in the opposite direction. Well, there's no option. There's no answer choice that has that, right? The official answer on the answer key for the AP College Board was C. Ball Y travel at a greater speed. Yeah, okay. In the same direction of travel as before the collision. But that's not correct, right? We know from our calculations that ball Y must travel in the positive direction, which is opposite from where it was going. So there is no correct answer for this question listed, but it should be greater than 5 in the opposite direction. So, hope that makes sense. I tried to, flag this question on the College Board website that it was wrong, but there's no option to do that, so hopefully someone will figure it out there at some point. All right, moving on. Number 12, in a one-dimensional perfectly elastic collision. This is important here. Perfectly elastic collision. An object with mass m is traveling with speed v0 in the positive x direction when it strikes an object with mass 3m that is at rest. What are the object's velocities following the collision? All right, now for this problem, we have to remember for a perfectly elastic collision, there are some special rules. There are two unknowns here, right? Let's set up our momentum conservation of momentum equation first. We have a mass m with a v0 speed plus 0, right? Because it's at rest initially. But after the collision, we're going to have mass m with some speed v, I want to call it v1f, plus mass of 3m with some speed, call it v2f, right? We don't know what those, either one of those things are. Looking for the velocities after the collision. We have two unknowns, right, that we're looking for. Well, we don't know what m is either, but at least, you know, we're not looking for m. So what do we have to do here? We're going to have to find, because m's would cancel anyway, I guess, right? We're going to have to find out what the velocities are using substitution with kinematics, kinetic energy, because this is a perfectly elastic collision, which means energy is conserved. So remember, there's a special formula, all right, that you can apply during a perfectly elastic collision. That formula is the v initial velocity of object 1 plus the final velocity of object 1 must equal the initial velocity of object 2 plus the final velocity of object 2, right? This is a rule that we know must apply in these special perfectly elastic collisions. Now, velocity initially of object 2 was 0. It was at rest, right? 0. And we know that the initial velocity of object 1 was just, we're calling it v0, right? So we're trying to solve, if you look at the answer choices, all the answers are in terms of v0. It's like 1/4 of v0 or 1/2 of v0, right? So we need to do it in terms of v0. So what I'm going to do is I'm going to solve for vf1, right? I'm going to solve for this guy right here. So how I'm going to do that, I'm going to subtract this v0 over here. I'm going to say final velocity of object 1, which is a 1m mass here, equals, let's subtract this over, so I get vf2 minus v0. So now the final velocity of object 1 is equal to the final velocity of object 2 minus the initial velocity, right? So now I'm going to take this formula here, and I'm going to plug it in, take all this guy here, I'm going to plug it in right there for v1f, since they're equivalent, right? Look, this is v1f, vf1, same thing. vf1 equals vf2 minus v0. This is vf1, right? So I'm going to substitute. So I'm going to have m v0 plus 0, right? So I'm not going to bother writing it, equals m, that m there, times v2f, or I'll call it vf2, whatever, it doesn't matter, f2 minus v0 plus 3m v f2, final velocity of object 2, right? So I'm looking for. So now what I'm going to do here now, I'm going to solve for the velocity of object 2, since now I only have one unknown variable, right? Again, I don't know the masses or v0, but masses are going to cancel, right? There's an m in every term, so m's can just cancel each other out. And then I'm going to have, I'm going to solve for vf2 in terms of v0, right? So this is going to be, I'm going to subtract, or I'm sorry, I'm going to add, rather, I'm going to plus v0 on this side, plus v0 on this side, so that's going to, these are going to cancel. It's going to be a v0 plus v0 is 2 v0s, equals, and I have vf2 plus 3 vf2. This is, add these up, right? It's 4 vf2. 4 vf2 equals 2 v0s. I divide by 4, and this is 1/2, right? So this is going to simplify down to v0 over 2 equals vf of object 2. So that means that object 2 is going to have a final velocity of whatever v0 was divided by 2. Well, and that's a positive value, so we know it's a positive direction. So we can rule out a here. Not going to be a, not going to be v over 3. So we really only ruled out 1 here, but that's okay. But now that we know what vf2 is, I can go back to this equation right here, and I can say, okay, well now I know that vf2 is v0 over 2, so that means vf1 that was the mass of object M, equals VF2 is V naught over 2 minus V naught, right? Now, this is like saying, this is V naught over 2, or like half minus 1. So what we're going to get is VF1 equals, one half V naught over 2, or half of V naught, minus 1 whole V naught is a negative half V naught, right? It's like saying a half minus 1. And what's a half minus 1? Well, you get negative a half, right? That's what we're doing here. So we know that the final velocity of object 1 is going to be a negative V naught over 2. And so negative means negative direction. So it's going to be, it's going to be D. And there we go. All right. That's the only one that had the negative direction. Okay. Number 13. Carts X and Y collide elastically. A graph of the magnitude of the force exerted on cart Y as a function of time t is shown. During which interval of time does the magnitude of the momentum of a car... During which interval of time does the magnitude of the momentum of cart Y change the most? Remember, this is a graph of force versus time. That area of the curve is impulse. Impulse is equal to, it is equivalent, it means the same thing as change in momentum. We're looking for where we have the largest momentum change, right? That's impulse. So which part of the graph has the largest change in momentum? Or in other words, the largest area of the curve? The answer is here between 0.04 and 0.06, or 0.004 and 0.06. Look at this area there, right? Shade that in. You see that that's pretty large area. Now if I do a different area, a different color, hot pink of course, from 0 to 0.02, let's see, this is 0.0, so this is 0 to here. Alright, that's not very big. That's a tiny little triangle. And then 0.08 to 0.10, that's, again, that's here, right? So those individually are pretty small. So the biggest area is clearly this one in the middle, this black area, right? From 0.04 to 0.06. That's the largest area. Largest area means largest impulse. Impulse means change in momentum, so it must be that area, right? Okay. Number 14. Am I still in hot pink? Yeah, let's stay in hot pink. Why not? I like it. Block X of mass 2 kilograms and block. This was a very this question everyone did pretty well on, so good job. Block X of mass 2 kilograms and block Y of unknown mass travel toward each other. An elastic collision occurs in which momentum is conserved. All right. The graph shows the velocity of block X and the velocity of block Y as a function of time before, during, and after the collision. What is the mass of block Y? So this is a straight up conservation of momentum problem. Can you interpret the data from the graph well enough to solve the conservation of momentum problem? So we're going to have m1v1i plus m2v2i equals m, and obviously a lot of you could, because like only a couple students got this one wrong, m1v1if rather plus m1vf plus m2v2f. Alright, so there we go. There's our setup. Now we just got to plug the numbers in the correct way. So it says block X is the mass of 2, block Y is the only mass. Let's make this an X and make this a Y. An X, make this a Y. Y. That way we know what we're talking about here. X. Alright, so X's and Y's. Alright, so mass of block X is 2. Its initial velocity from the graph, clearly before the collision, was 8. So times 8 there. Plus the mass of object Y, we don't know, so my. Times velocity initially of object Y, well, it's clearly a negative 2, right? So times a negative 2. Mass of block X is still 2 times after the collision. Now it's going, ooh, negative 7 looks like, right in between 6 and 8. So negative 7. Watch those negative signs. Plus mass of object Y times velocity after collision looks like it's going to be a positive 3. All right. So 3. Let's simplify things down. We got 16 minus 2my equals negative 14 plus 3my. So let's add 14 to this side. That gets 30. And then let's add 2 over here. That gets 5 my's, right? 2. I'm going to plus 2 my both sides. So 3 my's plus 2 more my's is 5 my's. Divide by 5. Mass of object y is going to be 6. 30 over 5 is 6 kilograms. That's the correct answer, which, again, many of you did get. So good job if you did. If not, it's okay. Now you know. All right, moving on. Number 15. We love this problem. You guys remember we did the skateboard stuff in class? So we got 2 astronauts. They're tied together by a rope, right? A taut rope. If you don't know what the word taut means, it means that it's like there's no slack in the rope, right? It's not like there's a dip in the rope. It's taut. It's not pulling on them, but it's like if you were to pull on it even a little bit, you were to pull, it would automatically transfer that force all the way down to the other person, right? There's no slack. It's not like going to tighten the rope. It's already tightened, it's taut. So we have these 2 astronauts. They're tied together by a rope, taut rope. One of them has this can in his hand, all right? And he's going to throw the can, I mean. And the question is in figure 1, which is figure 1 above shows the astronaut immediately after the container is thrown. So right as he lets go of the container, he throws it the moment after the container just left his hand, right? What happens to the astronauts? I'm not sure why the formatting is all weird when I copy and pasted this over, but anyway. Which of the following describes the motion of astronaut Y? So this is how is astronaut Y moving in figure 1 right after astronaut X throws it, and what's happening to astronaut Y in figure 2 right after astronaut Y catches the can. Okay, so remember we had the skateboard, all right? I mentioned this before in the video. If there's no friction, of course, in space there's no friction, or it's negligible. I throw an object, right? And what's going to happen to me? I'm going to go backwards, right? I'm giving positive momentum to the ball, or can in this case, so it has to go forward. It's got positive velocity, but momentum must be conserved. So if it gets forward velocity, I got to gain a little bit of negative velocity because momentum has to be conserved. So everything's got to cancel out, right? Now, obviously, I have more mass than that can or the ball, if I throw a ball, whatever. So I'm not going to have as much velocity as the can does because I have more mass, but I am going to have some negative velocity, right, going backwards. Well, if astronaut X throws the can forward, he's going to move backward, right? He has to, because that's how it works, right? He throws it forward, he moves backward, right? Conservation of momentum. But there's a rope tied between them. So the moment that astronaut X moves to the left, that rope is going to pull astronaut Y to the left also. So he's going to move to the left. Astronaut Y will move to the left a little bit right after astronaut X throws the can, because momentum is conserved. So when astronaut X moves back a little bit to the left, the rope is going to pull astronaut Y back to the left also. So we can rule out A and we can rule out C. Now let's look at between D and B. Now astronaut Y rather catches the can. Now when astronaut Y catches the can applies an impulse to the astronaut, right? To the right. So astronaut Y gets some change in momentum to the right, and astronaut Y applies a small impulse, equal and opposite, to the can to the left, right? Because he catches it. So what happens? Well, that means that the can stops, right? Because astronaut Y catches it. Remember astronaut Y was moving left, right? But he just had an impulse applied to him to the right. So what's going to happen? It's going to cancel out, right? The impulse to the right is going to cancel out his velocity that was to the left. So he's going to go back to where he was initially before any of this ever happened, which was at rest. So now it's not moving. So the answer is D. After the astronaut throws the can, they move left, but when they catch it, they both actually stop. So this is true for both astronauts, not just astronaut Y. It's actually true for astronaut X and astronaut Y. But anyway. All right, cool. Hope that makes sense. Let's go on to the next one. Number 16. Oh, I got a like on Twitter, you guys. I gotta check this out. Someone liked my tweet. Some dude. Okay, I don't know. All right. A student plans to conduct an experiment in which the momentum of a two-object system can be determined immediately before and after. This question is a mouthful, right? But it's actually really simple what it's asking. But let's read the whole thing to see what's going on. All right, so student, they want to plan an experiment. We got a two-object system can be determined immediately before and after the collision takes place. Okay, so he's got some apparatus where he can find the momentum of a two-object system before and after a collision. All right, cool. The student slides a block X at an unknown constant speed towards an identical block Y, that is initially at rest. there is negligible friction between the blocks and surface. Cool. The student then conducts a second experiment in which the magnitude of the force exerted on the block X from the block Y is measured over the time in which the collision takes place. A graph of the force as a function of the time is shown. All right, here's the graph of that impulse. All right, so let's area to the curve will be impulse. We know that, so keep that in the back of your mind. In a third experiment, the student creates a collision such that the force exerted on block X from block Y is constant. So it's not. See how this in this second experiment, the force is changing. Right, it's going from 0 to 150 to 325 to 475 to 650, 800, and then back down. Right, the force is changing. But in experiment 3, the problem says that this student is now going to conduct an experiment in which the force is constant. Right, it's not going to be unchanging force for 0.02 seconds. Which of the following constant forces, if exerted on block X from block Y, would produce the same change in momentum as shown in the graph? All right, well, we got to find out what the change in momentum of the graph is, right? So let's find that. So we're going to find the base of the triangle is 0.01 times the height of the triangle, which is 800, over 2. That's going to be 800 times 0.01 is 8, over 2 is 4, so the impulse is 4. All right, so impulse is 4. Now, so what I need here is, if the impulse here is 4, it's asking what force needs to be applied at a constant rate for 0.02 seconds to get the same impulse as I did in this collision, right? Well, the impulse is 4. So now I'm going to solve the equation delta P equals F times T. But I know what the impulse is. I just found it. So that goes in here. 4. I know what time is. It says it's going to be 0.2 seconds. 0.2. So I'm going to solve for F. So F times 0.2. I divide by 0.2. 4 divided by 0.2 is, as we know already, probably, 0.02. I was like, wait a second. All right, my bad. 0.02 seconds, and that is going to be 200 newtons. Right? Divide by 0.02. B. All right, cool. Moving on. Number 17, two carts of mass 2m and m approach each other head-on with the same speed v as shown in the figure above. When the carts collide, they hook together. Assuming that positive momentum is to the right, which of the following best represents the momentum of the cart, of mass m as a function of time before and after the collision? All right, so we have, let's do the conservation of momentum problem. So which graph is the most appropriate, right? I hopefully everybody ruled out A, because I mean, obviously the momentum is changing, right? It's not going to be constant because there's a collision. Now, if this were a graph of the total momentum of the whole system, then maybe it could be A, right? Because the total momentum of the system doesn't change. But it's asking us for a graph of just the momentum of cart of mass m, right? So just this cart. That's the only momentum we're trying to look at here, not the whole system. All right, so what happens to that cart's momentum? Well, let's see. We got 2m times v, or minus, rather, mv, right? Because this cart's going to the left initially. Equals. Now, after the collision, I'm going to add the masses up, right? Because they're hooked together. So they're one mass after the collision. So 3m times something, let's just call it vf. Now, we know that both objects are going the same speed before the collision. And we know that this object is going negative, right? Initially. So, that checks out, because all of our options that are remaining are all starting off with some negative momentum, right? Which makes sense because we're going negative direction. Question is, how does it change? How is the momentum going to change? Is it still negative after the collision? Does it get just a little bit positive, or does it go way positive like in D? Let's find out. So 2 mv's minus 1 mv's is just 1 mv, right? Equals 3 mvf. The m's cancel here. So I'm going to divide by 3 now. So I'm going to get vf equals v over 3. So it turns out that the velocity of this object here with mass m, well, both of them, right? They're hooked together, so it doesn't matter, is v over 3. Now, if this distance from here to here represents the momentum of an object with mass m and speed v, doesn't it make sense, negative v technically, doesn't it make sense if v is now 1/3 of what it was, v over 3, but now positive, it's going to be just a little bit above the axis, not way above. This distance here would mean that I have mass m and speed v, right? The same magnitude of momentum as I did before the collision, right? This much magnitude, that much below the x-axis. But I don't have that much momentum anymore. I know I don't have that much momentum because my speed is only 1/3 of what it was, right? My speed was v, and now it's 1/3 of v. So I can't have as much momentum, right? So I should be. It is positive though, not negative anymore. So I'm a little bit positive, a little bit above the x-axis, but not this much above the x-axis. So the answer is C. All right. 18. Oh, I love this problem. We got spaceship. This is a center mass problem. Spaceship and its shuttle pod are traveling to the right in a straight line with speed v, as shown in the top figure above. The mass of the pod is m. All right, so pod is this little shaded area here. This is the pod right there. All right, the shaded area. And the mass of the spaceship, the white triangle, is 6m, 6 times the mass of the pod. The pod is launched, and afterward, the pod is moving to the right with speed vp, or velocity of the pod, as shown in the figure. And the spaceship is moving to the right with speed, where its speed vf is greater than the initial speed, right? This speed of the spaceship after they separate is greater than it was initially, right, when they were together. All right, so it's an explosion collision, right? They're separating from apart. Which of the following is true of the speed vc, which represents the center of mass of the system after the pod is launched? All right, question. Before this happens, right, the center mass, say, is, I don't know, right here, okay? What's the velocity of the center mass before they separate? Isn't it just the same v speed as everything else? Right? They're all going together, right? Nothing's separated yet. Before the collision happens, before the explosion happens, or whatever it is. So the center mass here is traveling along with the spaceship and the pod together at the same speed everything else is going, right? So the speed is v. So before the collision happens, the velocity of the center of mass is equal to v, the velocity of the rest of the system, right? After the collision happens, ask yourself, was there any external force that did any work on the system? External. Nope. There's no external force. Whatever mechanism caused these objects to separate was internal to the system, right? It was a spring or some sort of, docking bay or whatever it is, because they're spaceships, I don't know, it doesn't matter. It was internal to this system, which means that the center of mass is in the exact same position as it was before, moving with the same speed as it was before, which is why the answer is D. The center of mass velocity is the same as it was before because nothing did work on the system, right? Now, if that's not clear enough for you, I'll say a little bit more about it. When this pod gets shot backwards, right, isn't it true that the velocity p is going to be less than v, right? So vp, velocity of the pod, is less than v, the original velocity. But also, vf is greater than the velocity v. So while the pod is slowing down, and some of the mass is going, it's kind of some of the mass is getting further away from the spaceship itself is actually speeding up, getting further away again from the pod. So where's the center of the mass? Where's the center of the mass? It's going to be in the middle, right? Somewhere in the middle, closer to the spaceship because it has 6 times the mass. But it's going to be, more towards this end. But it still has to go the same speed because it's got to maintain that position where it's in the middle of all the mass, right? 6 times mass in front of it and some mass behind it, but it's going to stay in that same position. Because there's no external forces. I hope that makes sense. I know that sometimes center mass can be hard to conceptualize, but basically the rule you want to remember is if there's no external force doing work on the system, nothing about the center mass changes. So whatever its velocity was, it's the same. Whatever its position was, it's the same. Sometimes you have questions where it's an object, something happens to the object, and the center mass will stay where it was. For example, say I have a grenade, okay? Center mass in the middle of the grenade. The grenade explodes and it goes in a million different pieces, all different directions, right? Well, after the explosion, where's the center mass? Well, was the center mass moving before the explosion? No. So guess what center mass is? Same spot. It never changes, right? Because there's no external force. The explosion from the grenade came from the grenade, right? So it can't change. The center mass would be in the same position. So that's kind of a good general rule to think of when it comes to center mass problems. Okay, almost done. Number 19. This is an energy problem. Block A of mass 2 kilograms is released from rest at the top of a 3.6 meter long plane inclined at an angle of 30 degrees as shown in the figure above. After sliding on the horizontal surface, block A hits and sticks to block B, which is at rest and has a mass of 3 kilograms. Assume friction is negligible. The speed of the blocks after the collision is mostly what? So first, it's a collision problem. before we figure out what the collision velocity after the collision is, we have to find out what the velocity before the collision was. We're going to use energy to do that. I think that's the easiest way to do it for me. Let's see here. There's actually a few ways you could do it. I'm going to find the height of this ramp. It doesn't tell us the height of the ramp, but we can find it, right? Because we have the angle, and we know that what the hypotenuse is. It's 2.6 meters long. I guess you could also do like kinematics, find out what its acceleration was, but I think energy is the easiest way to go about this here. So what we're going to do is, we know that sine of an angle is equal to the opposite side of the triangle divided by the hypotenuse. If it's a right triangle, and this is a right triangle, right? If we go straight down here, if I draw straight, all right, this makes a right angle with the horizontal. So sine of 30 degrees equals opposite over hypotenuse, which is 3.6, right? That's how many meters it is. Sine of 30 is a half times 3.6, both sides. These cancel. 3.6 times sine of 30 is 1.8. That must be the opposite side. Opposite side of the triangle is the height of it, right? So the height is 1.8. So how much energy do I have initially? Well, I have potential gravitational energy initially, and it's equal to mgh. All right, so we'll plug in the numbers here, find out how much potential gravitational energy we have. So UG will equal m, which was 2, g is 10, and the height was 1.8, we said. So multiply this together and see if we get 10 times 1 is 18, so 36. So 36 joules of gravitational potential. And as we go down the ramp, right, we're going to lose potential but gain kinetic. So by the bottom of the ramp, all the potential energy that was potential is now kinetic. So we're going to do kinetic energy now equals 1/2 mv squared. And all of this 36 is now in the form of kinetic because it transformed into kinetic energy. So 36 equals 1/2. Mass is 2. V squared. The half and the 2 kind of cancel, right? The half of 2 is 1. Square both sides. So V is square root of 36 is 6, right? I mean, am I crazy? Square root of 36 is 6. Yep. God, I have OCD about that. I gotta punch it in. All right, so velocity is 6. Now we can actually do finally we can do the momentum conservation of momentum equation. So m1v1i plus 0, because it's at rest, equals, they collide and stick, right? So m1 plus m2 times vf. All right, so m1, that's block A, mass 2, times, now we know velocity initially was 6, because we solved for it, equals 2 plus 3 is 5 total mass times vf. 2 times 6 is 12, equals 5 vf. We divide by 5, and it's cancel, and we get 2.4, right? 2, yeah. 2 2/5, which is vf equals 2.4 meters a second, which is our answer. And there we go. Very good. All right, last problem. The multi-answer question, number 20. A cart of mass 1 kilogram travels along a horizontal frictionless surface. A net force is applied to the cart. A graph of the magnitude of the net force applied to the cart as a function of time is shown. Cool. The initial and final direction of the cart and the direction of the net force exerted on the cart is unknown. The distance of one grid unit represents a change in velocity of 1 meter per second. It's talking about down here on these things, right? Which of the following diagrams could represent the direction and relative magnitude of the velocity of the cart before the force is applied and after the force is applied? Select 2 answers. All right, so the key here is to find the impulse, right? So let's do that first. Impulse is going to be the base times height over 2, because it's a triangle. Area under the curve, right? So base is 2, height is 4. So 2 times 4 is 8. Divided by 2 will be, area of the triangle is going to be the base times height over 2. So height is 4, base is 2 over 2, so it's going to be 4. So our delta P is then 4, right? Okay. Now, if it's a 1 kilogram cart, okay, what I'm going to do now is I'm going to say, okay, well, I know that delta P equals mass times change in velocity, all right? I know my delta P is 4. I don't know what direction it's in, because I don't know what direction the force was, right? It says the final direction of the force is unknown. That's why there's 2 answers, right? But its magnitude is 4. So if the impulse is 4, if the mass is 1, then that means that let's solve for delta v then, right? We divide by 1, okay. Delta v is 4, right? That means my change of velocity is 4. I'm either gaining 4 velocity if the force was, applied in the positive direction, or I'm going to be losing 4 velocity if the force is applied in the negative direction, or against my initial velocity. So which two of these 4 options has a change velocity of 4 meters a second? Remember, it said that each square in the grid represents 1 meter a second. So I'm basically looking for the 2 options that have a change velocity of 4, right? So this one is 1. This is, a change in 4. Excuse me, I'm getting ahead of myself. So this one was -1 beforehand, and now it's 1, 2, 3. So it's 3. So is that a change of 4 from -1 to 3? Final minus initial. 3 minus a -1 is, that's a change of 4, right? So that seems good. And now B is a -1 and a +1. Is that a change of 4? Final minus initial. 1 minus -1. That's a change of 2. That ain't 4. Can't fool me. All right. At rest, okay, 0 to 1, 2, 3. That's 3. So final minus initial, a change of 3. That ain't 4 either. So now it's got to be D. But let's look. This is a +1. And then we got 1, 2, 3, 4, 5. All right. So 5. So final 5 minus initial 1. Yep, that's also 4, right? So we know it's got to be D. So A and D are the answer, because those are the 2 options that showed a change of velocity of 4 meters per second. And we're done. We did it. Hopefully that was not too terrible for you. All right, guys. Thank you for going through that. And make sure you do your corrections. Try your best to articulate what you didn't understand or what you were confused about, or what have you, on each question, and then correct it appropriately. I will see you guys in class when I see you. Email me, text, remind anytime, because I don't have a life. You are my life. Bye-bye.